Hello and welcome back to the course on artificial intelligence. In today's section, we're tackling the topic of deep Qlearning. So let's see how we're going to attack this. In this section, we will learn a deep Qlearning intuition, the learning side of things. So we're going to separate deep Qlearning, the intuition behind it, into two parts, the learning and the acting. And we're going to have two tutorials on that. So first we'll understand how the neural networks actually learn and how they update their weights based on what we are feeding them in and how the whole concept of Qlearning works. So how we're going to take the temporal difference concepts that we discuss in simple Qlearning, we're going to apply them into deep Qlearning. And then we're going to talk about how deep Qlearning algorithms actually decide what action to take in what states. Then we're going to talk about experience replay, a very important addition on top of deep Qlearning, which actually enables deep Qlearning to work properly, and you'll see why it's important from that tutorial. And then we're going to talk about action selection policies. We're going to talk about how deep Qlearning agents are able to combine exploration with exploitation. So once they found something, a good approach, they can use that approach, but also they need to explore so that they don't get stuck in a local maximum. And one more thing I wanted to mention about this section is it is highly beneficial if you have a look at Annex number 1, artificial neural networks. So if you go and explore all those topics, we've got some very powerful intuition tutorials prepared for you there. If you haven't done the deep learning course, if you've done the deep learning course, then you already know all of these things and you can proceed with the section. But if you want to get that additional knowledge about neural networks before you proceed with this part of the course, this is highly advisable because it will help you understand exactly how neural networks work and why they're so powerful, why we're leveraging them in this deep Qlearning algorithm. And once you've refreshed your knowledge or gained that knowledge on neural networks from that annex, then come back here and we will proceed with the deep Qlearning. If you're pretty comfortable with neural networks, then let's get straight into it. Let's start talking about deep Qlearning intuition. And I look forward to seeing you on the first tutorial. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. And finally, we're on to the fun stuff. We're on to deep Qlearning. All right, so let's have a look. Previously, we spoke about Qlearning and what it's all about, and we learned about the agent, the environment, and how the agent will look at the state he or she is in, take an action, get a reward, enter into a new state, and based on that feedback loop, they will continue taking actions, and they'll learn from that, understand what are the better actions to take. And so we looked at this basic example of a maze. We understood that as the agent explores the environment, it understands what the values of the states are. Then we moved on from dealing with the values of the states to dealing with the values of the actions or the Q values. And then based on that, we understood how plans in non-stochastic environments work and how policies work in stochastic environments. And this is an example of a policy. So that's a quick recap of everything we discussed in the basic Qlearning. And now let's have a look at how this can be taken to the next level through deep learning, through adding deep learning. Okay, so this is our environment. And what we're going to do now is we're going to add, instead of just doing basic calculations in this matrix that we have, which is pretty simple, what we're going to do is we're going to add two axes. We're going to add an X and Y axis, or we'll call them X1 and X2, just to make things even more general. And here we've got we'll number the columns 1, 2, 3, 4. Here we'll number the rows 1, 2, 3. And so now every single state can be described by a pair of two values, X1 and X2. So any one of these squares in which the agent can possibly be in can be described by X1, X2. So for instance, right now he's in the square with X1 equal to 1 and X2 equal to 2. And therefore, that's in that same way, we can describe any square, meaning we can describe any state. And of course, this is a very simplified version of an environment of describing states, but nevertheless, it works in this case. And that means that now we can feed these states into a neural network. And by the way, here, I would just like to mention that at the end of the course, we've got annexes. We've got annex number 1 and annex number 2. In order to proceed successfully with this section, it's highly advisable that you check out annex number 1, which is on artificial neural networks, so you understand how they work, so that we don't have to delve into that here, and we can just use the benefits of the knowledge of how artificial neural networks work. And so we feed in this information on the state into a neural network, and then it will process this information, so x1 and x2. Depending on the structure of the neural network, it might have multiple hidden layers and so on. So that's something that you'll figure out in the practical tutorials. But at the end, we will structure in such a way that it spits out 4 values. And these 4 values are actually going to be our Q values. So the values which dictate which action we need to take. And further down in this tutorial, we'll see exactly how these Q values are used to decide which action is taken. But the main point here is that we no longer look at just this maze from a Qlearning perspective. We're now taking the states of the maze and we're feeding them into a deep neural network in order to get these Q values. And at the end of the day, we're still going to come up with an action. We're still going to understand what action we need to take, and we'll discuss all this in more detail. But the question right now is why? Why are we doing all of this? Why are we making things so much more complicated when that initial approach of Qlearning was working already? Well, the reason for that is the Qlearning was working in this very simplistic environment. And we're continuing to deal for now with this very simplistic environment in order to better understand the concepts. But at the same time, that simple Qlearning will no longer work in more complex environments. And we're talking about, for instance, the self-driving cars, which you'll be creating, or playing Doom, when the artificial intelligence is playing Doom, or other Atari games like Breakout, or even self-driving cars and more advanced reinforcement learning things such as like robots walking around and performing actions. In all those cases, basic Qlearning is insufficient, is not strong, is not powerful enough to be able to master those challenges. And just like we've seen in the deep learning course, if you've been in our deep learning course, or if you've done the annex sections, annex number 1 and annex 2, you will already know that deep learning is by far superior to any type of machine learning, let alone simple Qlearning. And that's why we're leveraging the power of deep learning here. So we're feeding in the information about the environment as a vector of values, so in this case just 2 values, into a deep neural network, and then we're using that to perform the actions that we want to decide which actions the agent's going to take. So that's kind of like a high-level overview of why we're doing this. And now let's have a look at, in a bit more detail, at what happens to the concepts of Qlearning when we make this transition from simple Qlearning into deep Qlearning. So as you saw in the previous intuition tutorials, we had a slide like this, which is the foundation of temporal difference learning. This is the formula for temporal difference. And basically, so let's go through this. So basically, we had an agent who was in this state over here, which is indicated by blue arrow. And we were understanding how temporal difference works for this Q value of, for instance, going up. And so what we saw here was before, this is in the simple Qlearning, not the deep Qlearning, this is in the simple Qlearning. What we saw was before, the agent had a certain Q value that he had learned about this action of going up. And so then he decides to take this action to go up. And right after he takes this action, he gets a reward for taking this action in this state. And that is that reward. Plus, now he can evaluate the value of the current state he's in, which is the maximum of all of the new Q values of the new actions he can take, A prime, in the new state S prime. And we multiply it by the decay factor of gamma. So that is essentially the new Q value, or kind of like the empirical Q value that he has just received for taking that action. And ideally, these two should be the same. So the Q value that he had in his memory about this action in this state, it should equate to the actual reward plus the gamma times the value of the state that he ended up in. And therefore, that's how we calculate the temporal difference. We take what he got after minus what he had in mind, what he was expecting. You subtract one from the other, and that's your temporal difference. And then you use your learning rate alpha to adjust your Q value, your new Q value by the temporal difference, but with a coefficient of alpha. So that is the essence of the simple Qlearning. Now let's have a look at how it changes in deep Qlearning. And so we're still going to work with this slide, but we're going to just see exactly what's happening. So in deep Qlearning, the neural network will predict 4 values. As we saw in the previous slide, and as we'll see further down in this tutorial, the neural network will predict 4 values, or it might predict more values if there's more possible actions in a given state. But in this case, we know that there's only 4 actions: up, right, left, or down. And so the neural network will predict 4 of these values. So there will be no, in a deep Qlearning situation, it's important to understand there's no before or after. And this is how we'll get to know this a bit better. So the neural network will predict 4 of these values. And it will compare not to what will happen after, but the neural network will compare to this exact value, but it was this value which was calculated in the previous step. So in the previous time when the agent was in this exact square, so let's say, I don't know, some time ago, the agent was in this exact square as well, and it calculated this value previously. So in the previous time, a long time ago, the agent calculated this value. Then the agent stored this value for the future. And now the future has come. So now he's in the square again. And now he's got these Q values, which is predicted. And one of them is for going up. So now what he's going to do is going to compare the predicted value of Q to this value which he had recorded from the previous time. And we'll understand exactly why this is important right now. So just important to understand here is there's no before and after in this specific square, this specific time. We're taking the Q value that he's predicted using the neural network this time, and we're comparing it to this value which he had from the previous time. From the previous time he was in this square, assessing all of the situation, and the previous time he actually performed this action. So there we go. Now let's have a look at how this all works out in the neural network and why is it like that. I know it sounds a bit complicated right now, but we'll break it down into simple terms right just in a second. So this is our neural network. We're feeding in the states of the environment into the neural network. It's going through the hidden layers. Then it's coming out with these outputs, Q1, Q2, Q3, Q4. In that specific state, these are the Q values that the neural network is predicting for the possible actions. Those are the Q values. So then we're comparing to target. And these targets is exactly, so if we go back here, this is the target. So this is the value that was predicted. And then, but also we know that we have a target from the last time we were in the square. We have a target for this same action, which is up, for instance. So here we've got a target and we're going to compare. So we're comparing Q1 versus that target. We're comparing Q2 versus that target, the target that we had from previously. Q3 versus the target, Q4 versus the target. And so this is the part where the neural network or the agent is now learning through deep learning how to better go through this maze. And the key point here is that we're still applying Qlearning, but the concepts in simple Qlearning you learn through temporal differences, which are pretty straightforward, which we've already discussed and we know quite well by now. But at the same time, in deep learning, how do neural networks learn? Well, neural networks learn through adjusting their weights. So we have to adapt the concepts of simple Qlearning to the way neural networks actually work, and that is through updating their weights. And so this is what we're trying to figure out here. How do we adapt that concept of temporal difference to a neural network so that we can leverage the full power of neural networks? And so far we've gotten this. So we enter our environment state here as a vector, goes through a neural network, we get predictions of Q values, and then from the previous time the agent was in that state, we have these Q target 1, 2, 3, and 4 for each of these respective actions. And so now we're up to, okay, let's compare each one with each one. And from here, it becomes pretty straightforward if you're up to speed with neural networks. Once again, that's all in annex number 1. We're going to calculate a loss, which is L here, and we're going to be Q target, this one, minus Q, minus this one. We're going to square that, so the square difference of each one of these, and we're going to sum them. So we're going to take the sum of the squared differences of these Q values and their targets, and we're going to sum them up, and that's going to be our loss. And so ideally, just as we had in the temporal difference learning, so if we go back for a second, remember we said ideally we want this to be equal to this. So we want the temporal difference to be 0. So that means basically the agent is predicting exactly correctly what, the Q values that the agent is predicting are exactly, or that he has in memory, are exactly descriptive of the environment, and therefore the agent can navigate the environment pretty well, right? There's no surprises. There's no as long as this temporal difference is highly positive or highly negative, then we've got some surprises. But if the temporal difference is 0, then he knows the environment so well that he can predict what's going on, and therefore his policy is going to be very good, and he's going to be able to navigate it. So here, same thing. So we want this loss to be as close to 0 as possible, as small as possible. And that's why now this is the part where we are going to leverage the real true power of neural networks. So we're going to take this loss and we're going to use backpropagation or stochastic gradient descent to take this loss and pass it through the network. Pass it back or backpropagate it through a network, and through stochastic gradient descent, update the weights of these synapses in the network. So that next time we go through this network, the weights are already a bit better descriptive of the environment. And that's exactly how it works. So here you have, if we go back, this is calculated, loss is calculated, and it gets propagated for the network. The weights are updated. Then the next time we get here, this happens again. And we get here, this happens again, and so on. And it keeps happening, and that's how this agent learns, or basically now it's a neural network, which is the brain of the agent, is learning, is becoming more and more descriptive of the environment, and therefore the agent is able to navigate the environment better. When we say descriptive environment, basically means that when we put in the states of the environment that the agent is in, we are more likely to get closer and closer to the actual Q values. And that happens because the Q values that we want and find the right action. And that happens because these Q targets are actually empirically derived. So how does he find these Q targets? That's actually this. So he actually observes, okay, so once I do take this step, what's the reward I get? And then what's the value of this state? So same thing as we saw previously in Qlearning, in the simple Qlearning intuition. So he learns this through trial and error, and then he constructs his network or updates the weights of his network in such a way that the predicted Q values are closer and closer approximating the target Q values. So very similar to the concept we discussed here in the simple temporal difference learning of the simple Qlearning algorithm. So there we go. That's how the agent learns. So we're up to here. That's the learning part. Hello and welcome back to the course on AI. In the previous part, we talked about the deep learning, Qlearning intuition. We started there, and in fact, we actually got all the way to this part, and where we talked about learning. And now we're going to move on to the actual acting part. So there's two distinct parts that we have to remember. So that's the learning part, but now he's done all of this. That's beautiful. Now he actually has to take an action. He has to decide what is he going to do. He's going to do action 1, 2, 3, or 4. And so how does he do that? Well, the way he does it is now, given those same Q values, so the Q values don't change. After we have these Q values, we've compared them, we've calculated the loss, we've backpropagated the error, we've updated the weights, but the Q values don't change in that whole process. So after we've got the Q values, they're fixed. We know what they are, so all of this happens, the network's updated, and now using those same Q values that we had, what we're going to do is we're going to pass them through a softmax function. And again, softmax is described in Annex 2, and we'll talk a bit more about softmax further down or we'll talk about this action selection policy further down in the rest of this section, so just in a few tutorials. But for now, we're just going to say we're passing it through a softmax function, and basically what it does is it helps select the best one. It selects the best action possible. There's a small caveat to that. It's not just the best one possible. We'll talk about that in the action selection policy tutorial. But for now, let's just say it selects the best action from here. It says, okay, so Q1, the likelihood, basically we know the Q values. So it's predicted the Q values, so it can look at them and say, okay, so the highest Q value out of these, just as we did in the simple Qlearning algorithm, it'll just look at all these 4, say the highest Q value is this one, and I'm going to select that action. I'm not going to take those. And that's pretty much it. That's how it chooses which action takes the action, and then all of this process happens again for the next state the agent ends up in our case, in the next square of the maze. But generally speaking, it's the next state. So there we go. That's how we feed in a reinforcement learning problem into a neural network through a vector describing the state that we're in. And once we feed it in, there's two parts of the process that happen. Part one is the learning. So remember that part where we compare each of the Q values with the targets, and then we backpropagate the loss through the network to update the weights so that our network is learning as we go through this maze or through this environment. And also the second part is, of course, we have to act. We have to select an action. And that is where we pass the Q values through the softmax function or basically an action selection policy, which we'll talk about further down. And then we simply select the action that we want to take and we perform that action. And then this whole process starts again. And then maybe the agent gets to the end, maybe the agent doesn't pass the game. In any case, the game ends. And then once again, the whole process repeats. The agent plays the whole game again. And then that stops. So basically that's another epoch. Every time the agent, every time the game ends, whether favorably or unfavorably, that's the end of an epoch, and then he starts again, and then he starts again, and then he starts again, and so on. So that happens, and this process happens for every single time the agent is in a new state. So the state is encoded here. So that's important. So not just for every single game that he plays, but for every single state. So he's in a state, it goes through this process, updates, and so on, and happens every single time. And so the learning happens, and then the acting happens as well. So that is deep Q learning or the intuition behind deep Q learning. We've got lots more to cover off. And then, of course, we've got the practical. And in the meantime, if you'd like to get some additional information on deep Q learning, we've got a recommended reading. So we've already spoken about Arthur Giuliani's series of blog posts. If you look at simple reinforcement learning with TensorFlow Part 4, you will find the part that's relevant to what we discussed today. Note that here he talks about convolutions. We are not covering convolutions in this section. We're going to be talking about them in the next section of the course. So the difference here is that, so just kind of skip the convolutions part for now, and we'll talk about them in the next part of the course. But the difference is in convolutions, you're like your agent is looking at the image, and therefore he has to process an image, so an additional complication. For now, we're slowly, gradually building up to that. For now, we're encoding our environment through, so if you look here, we're encoding our environment, or maybe like look at this one probably, encoding our environment or encoding a state the agent is in as a vector. So in our case, it was a very simple vector of two values. Sometimes people, even in that simple maze, sometimes, or as you'll see from this blog post, sometimes people prefer the one hot encoded version of that state. So basically where every single box of the maze has so you have like a vector of, in our case, it would be 12 values, 3 by 4. So it's like either 1 or a 0, depending on which element, in which box you're in the environment. So in whichever way you decide to encode your environment and the state of your environment, that's how we're encoding it. So it's basically a vector. The key here is that it's not a convolution. So it's not like an image and there's no convolution involved. So this part will come later. For us, it starts over here. And that just simplifies the process for us to gradually understand better. And of course, don't forget that this blog post is written in TensorFlow and we're using PyTorch in our tutorials. So hopefully you enjoyed this quick intro into deep convolutional deep Q learning. And on that note, I look forward to seeing you next time. And until then, enjoy artificial intelligence.